initial insight into the universe. The new window would unveil not only the architecture of the Milky Way, but also a multitude of novel astronomical phenomena, including pulsars. Jansky constructed an antenna capable of detecting radio waves with a wavelength of 14.5 meters. To enable him to ascertain the source of the static, he affixed the antenna to a large turntable, which garnered the designation Jansky's merry-go-round. After months of observation, Jansky could differentiate static from nearby and distant thunderstorms. However, what captivated him was a subtle yet persistent hiss that appeared to emanate from an indeterminate source. Due to the daily fluctuations in static intensity, Jansky initially believed he was detecting static from the Sun. Due to Earth's rotation occurring once every 24 hours, the Sun traverses the sky consistently throughout the year. However, after months of observation, it became evident that the most luminous point was shifting, not in a regular 24-hour cycle as observed with the Sun, but in a shorter duration of 23 hours and 56 minutes. The distant stars experience a loss of 4 minutes daily due to the Earth's orbit around the Sun. The discrepancy was minimal, yet sufficient to ascertain that the origin was celestial and extrinsic to the solar system. The static discovered by Jansky originated from deep space. Initially, Bell Labs leveraged the discovery and garnered extensive publicity. When Jansky proposed the construction of a 30-meter diameter dish antenna to further investigate the phenomenon, he received no support from his employer. Although space-based static intrigued Jansky, it presented no challenge to Bell Labs' operations. They received their response, and that concluded the matter. Jansky was assigned a different project and subsequently never returned to radio astronomy. The radio sky was overlooked for years. In 1934, a young Grote Reber perused one of Jansky's papers and believed he had discovered the solution for conducting a more thorough investigation of the phenomenon. Constructing a parabolic dish will facilitate the examination of these unusual radio emissions at elevated angular resolutions, thereby accurately identifying their sources in the sky. Reber communicated his proposal to Jansky, but Jansky responded unfavorably for ambiguous reasons that need to be clarified. Reber could have contacted the astronomers more responsively. In a 1992 interview, he stated, "The optical astronomers were ignorant of radio technology and thus deemed Jansky incorrect, while the electrical engineers acknowledged Jansky's research but found it irrelevant." However, not all dismissed it as futile. Within a few years, Cambridge physics professor Gennady Potapenko and his student Donald Follard validated Jansky's discoveries, utilizing a loop antenna and subsequently a single-wire antenna in the Mojave Desert. 1936, despite Jansky's discouraging response, Reber built a 31.5-foot fully steerable parabolic dish in his parents' backyard. Assisted by a local blacksmith, the total expenditure amounted to $1,300, enabling him to investigate the radio sky at wavelengths of 74.9 cm, 400 mmHz, and 199.9 cm, 150 mmHz. Reber became the inaugural and sole radio astronomer globally with this apparatus. Regrettably, scholars rejected his work due to the absence of appropriate university academic oversight. Significant advancements included identifying sunspot groups at radio wavelengths and the forecast by discovering the crucial 21 cm line emission attributed to hydrogen. The latter was a crucial advancement in elucidating the dimensions and structure of our galaxy. Numerous acclaimed publications assert that gazing towards Sagittarius allows one to observe the center of the Milky Way galaxy. This is akin to asserting that if I gaze at the ground beneath me, I observe Greenland. Local geography can be modified accordingly. Vast clouds of interstellar gas and dust separate us from the remainder of the galaxy, making the endeavor to map our surroundings akin to navigating through a dense fog at night while wearing sunglasses. In the mid-1940s, the eminent Dutch astronomer Jan Oort contemplated the feasibility of investigating interstellar hydrogen, which comprises most of the galaxy's composition, at radio wavelengths. He assigned his student Hendrik van der Hulst to explore the feasibility, and in 1945, Van der Hulst provided the solution. At a wavelength of 21 cm, hydrogen emits a distinct spectral line. Should a radio receiver be constructed to detect solely this wavelength, hydrogen would become observable, and the obscuring dust and gas of the Milky Way would become transparent. Van der Hulst indeed presented the proposal to Reber. Reber commenced the construction of an antenna for the task, but was subsequently offered a position with the National Bureau of Standards in Washington. He relinquished the undertaking. Harold, Doc, Ewan and Edward Purcell took 6 more years to ultimately discover the 21 cm line. With the obscuration of interstellar gas and dust finally removed, astronomers could delineate the galaxy's structure, unveiling its spiral configuration. For the first time in history, astronomers could examine beyond the limits of the local stellar vicinity and investigate the galaxy. More significant to this narrative was the progressive enhancement of radio technology that facilitated the identification of discrete radio sources, which are compact and distinguishable emitters of radio waves, separate from the ambient radio background. Throughout the Second World War, radio technology experienced significant advancement, and by the war's conclusion, radio engineers in England, Europe, the United States, and Australia were directing their focus and antennas toward the sky. The initial intense radio emissions from the Sun were inadvertently detected by British coastal radar stations during the war, and were mistakenly ascribed to German jamming efforts. James Stanley Hay examined the phenomenon and accurately deduced that the Sun was emitting radio waves. In 1946, he conducted one of the initial meter-wavelength sky surveys, during which he identified a prominent discrete radio source in the constellation Cygnus. However, he could not precisely determine its location for optical identification. The majority of the significant early discoveries occurred in Australia. From Dover Heights, situated on the eastern coast of Sydney, John Bolton, Gordon Stanley, and Bruce Slee employed equipment on the cliffs that overlook the Tasman Sea. Similar to the way the ascending sun sparkles upon the water, each radio object emerging over the ocean's horizon produces a reflected image on the surface, resulting in 2 sources of radio waves that intermittently amplify and diminish one another. This phenomenon can be illustrated by dropping 2 stones into a tranquil pond and observing the 2 sets of waves as they alternately interfere and enhance each other as they propagate across the surface. Radio waves exhibit analogous behavior. By calibrating the radio antenna to capture both wave sets, the engineers could approximately determine the celestial position of the source based on the intensity, rise time, and periodicity of the resultant interference pattern. This method, called interferometry, was set to assume an increasingly significant role in radio astronomy in the forthcoming decades. The team at Dover Heights prioritized re-identifying the source in Cygnus, as reported by Hay in 1946, and aimed to determine a significantly more precise location for it. In June 1947, they identified its C interference pattern and designated the source Cygnus A. However, its location contained only a few dim stars. Bolton and his team deduced that a singular radio source indicated the existence of additional sources, prompting them to survey the skies using their C interferometer. On November 6, 1947, they discovered another source in Taurus, and by March 1948, they had identified an additional 6 sources dispersed throughout the sky. Radio sources do not resemble stars. Although individual stars are easily identifiable, the positions of radio sources could have been more precisely defined. Like Cygnus A, none of the other radio sources corresponded to objects observed at visible wavelengths. Cygnus A, the most robust of the sources, was identified in the early 1950s by a team led by Francis Graham Smith in Cambridge, whose more precise location aligned with a relatively dim nebulous area. Walter Baade and Rudolf Minkowski utilized this position to conduct a spectroscopic analysis of the visible object, identifying it as a galaxy and determining that it predominantly emitted energy in radio wavelengths. In mid-1948, Bolton and Stanley journeyed to New Zealand to enhance the resolution of radio sources. They possessed 2 objectives. One could observe the sources positioned over a Western Ocean horizon, enabling a more precise determination of their location. The second point is that New Zealand possesses cliffs of greater height than those found on the east coast of Australia, and it was anticipated that the increased elevation above sea level would enhance angular resolution, yielding a clearer radio image. Transporting an aerial on a substantial trailer, they chose two clifftop locations with elevations of approximately 300 meters, in contrast to Dover Heights at 79 meters. Notwithstanding the recurrent extreme weather conditions, 4 months of observation and analysis disclosed the locations of 4 new sources within mere minutes of the arc, approximately 1/6 the diameter of the full moon. 2 sources corresponded with optical images of galaxies. The location of Virgo A aligned with a massive elliptical galaxy known as M87, the second brightest constituent of the 2,500-member Virgo cluster of galaxies. Centaurus A was associated with NGC 5128, which subsequently demonstrated to be a significant source of X-rays, infrared, and gamma radiation, as well as the closest of the so-called active galaxies. Taurus, a third radio source, corresponded with a millennium-old supernova remnant known as the Crab Nebula. The Crab Nebula is named for its outline, which loosely resembles a crab. The minute illumination area, observable through small telescopes, aligns with the sight of a new star documented by Chinese and Japanese astronomers in 1054, who noted its visibility even in daylight for over 3 weeks. When Bolton discovered, the disparate elements of stellar evolution began coalescing. The new star was a supernova, the violent and dramatic demise of an aging high-mass star. Nearly 900 years later, it continued to emit radio waves throughout the galaxy. Aside from the Sun, the Crab Nebula was the inaugural visual object recognized as a radio source, thereby establishing John Bolton, Bruce Slee, and Gordon Stanley as the pioneers in correlating radio sources with optical counterparts. This also signified the maturation of radio astronomy, demonstrating that it could yield discoveries entirely independent of optical astronomy. A novel epoch in scientific inquiry has commenced. Australians were not the sole participants in the emerging domain of radio astronomy. John Ratcliffe, a prominent authority on upper atmospheric physics, returned to Cambridge University in England following the war's conclusion. During the war, Ratcliffe focused on radar research. Upon his return to Cambridge, he enlisted several young radio scientists, including Martin Ryle, Francis Graham Smith, and Anthony Hewish. The men recovered as much British and German radar apparatus as feasible over a year, and subsequently initiated radio observations. Following the observation of sunspot emissions, the team concentrated on specific radio sources. Although the Australians were the pioneers in discovering these sources and conducting preliminary sky surveys, the British team executed the first extensive surveys of the sky in pursuit of new objects. The inaugural Cambridge survey, now comprising 9 published surveys, employed a technique known as phase switching, developed by Ryle. This entailed capturing signals from 2 distantly positioned antennas and introducing a delay to one, causing it to alternately align and misalign in phase with the signal from the other. This technique facilitates the more straightforward identification of point radio sources against the background. Employing this technique, the Cambridge team successfully catalogued 50 sources. In 1952, 4 years later, Ryle directed a team that employed a double interferometer, comprising 4 cylindrical antennas, at the corners of an expansive field located a few kilometers west of Cambridge. After 3 years, the astronomers catalogued 1,136 radio sources in the 2C catalogue. However, the third Cambridge catalogue, or 3C, was set to unveil a completely novel astronomical phenomenon. A particular type of radio source distinguished itself from all others. Perceived against the sky, they appeared diminutive yet luminous, the radio counterparts of stars, prompting astronomers to designate them as quasi-stellar radio sources, subsequently abbreviated to quasars. A radio telescope's resolution is significantly inferior to that of optical telescopes, making it challenging to ascertain both the point-like nature of quasars and their precise locations. Both elements were elucidated in 1962 when the Moon obscured the brightest quasar, 3C273.5. As the Moon orbits the Earth, it eclipses any celestial object more distant than itself, a phenomenon known as a lunar occultation. Due to the Moon's lack of atmosphere, its edge or limb appears distinctly defined when observed from Earth. When the Moon occults a point object such as a star, the star abruptly disappears instead of gradually fading, as occurs with objects with a measurable diameter, like planets in the solar system. The technique of lunar occultations was initially employed to determine the Moon's position. By precisely knowing the positions of the stars, the Moon's trajectory could be accurately mapped. Determining the exact position of the Moon allows for the inverse process. By documenting the moment a radio source is obscured by the Moon, one can unequivocally ascertain the location of the radio source for correlation with observable entities. In the early 1960s, several attempts were made to identify these peculiar radio sources, yielding limited success. The advancement occurred in 1962 with the utilization of the 64-meter Parkes radio telescope in western New South Wales. Every 20 years, a series of occultations of 3C273 is observable from the southern hemisphere. Cyril Hazard, then affiliated with the newly established astronomy group at Sydney University, reserved time on the recently completed Parkes telescope to observe the occurrences. The initial observation required greater conclusiveness. An additional occultation of 3C273 remains unobserved due to an issue. The substantial diameter of the Parkes dish, in contrast to its comparatively short support tower, restricted the dish's tilt to a maximum of 60 degrees from the zenith. An alarm activates when the large dish attains an angle of 30 degrees above the horizon and its rim nears the ground, causing the telescope to halt automatically. The issue was that when 3C273 was set to reappear from behind the Moon, the two objects would be positioned slightly below 30 degrees in the sky. This was a significant observation pertinent to the radio astronomers and the Parkes telescope. The newly completed telescope was anticipated to commence its operations with a significant discovery, and quasars offered substantial potential. Bolton and his colleagues would not allow a trivial safety protocol to impede a potentially significant astronomical discovery. Bolton dismantled the telescope's safety mechanisms and utilized a grinder to excise portions of the bearing housings, enabling the dish to tilt an additional degree toward the horizon. In preparation for the observation, all access roads to the observatory were closed. Non-essential electrical equipment was deactivated, and the electronic equipment required for the observation was duplicated. On the evening of August 5, 1962, 3C273 was obscured by the Moon. Upon re-emergence, the Parkes telescope's edge was nearly in contact with the ground, yet they observed everything. The observations were so significant that Hazard and Bolton returned to Sydney with duplicate copies of the event's records on separate aircraft. Upon analysis of the radio observations, it became evident that 3C273 comprised two distinct points rather than one. A subsequent comparison with photographs of the region captured by the 200-inch Hale telescope revealed that the radio source coincided with an inconspicuous blue star, exhibiting a faint jet extending from it. At this juncture, most astronomers posited that these radio stars were anomalous stars residing within the Milky Way, akin to other stellar bodies. The subsequent step investigated this star that appeared unusual in photographs and exhibited intense radio emissions. As demonstrated, stars are analyzed via their spectra. A Dutch astronomer, Martin Schmidt, employed the 200-inch telescope, the largest in the world at that time, at Palomar Observatory in the United States to successfully acquire the spectrum of 3C273, thereby enhancing the understanding of quasars. Analyzing the spectral lines was anticipated to provide astronomers with insights into the star's composition, motion, and other characteristics. However, after examining the line's configuration,